Okay, so let's see how we can prove this using something called analysis. So this is a very general, useful tool. We can think of mathematical analysis as the use of inequalities to prove things. I'm probably not doing it justice by giving it such a simple definition, but in the context of machine learning, analysis is usually where we somehow use inequalities toward the end of showing something that we want to prove. So we can use analysis to prove that the argmin over all vectors w of the squared L2 norm of w, subject to the constraint that the vector w must satisfy xw equals y. So the vector we get to pick has to satisfy our linear equation, our linear problem. The minimum of that is equal to the least norm solution, which I defined on the previous slide. So let's look at the proof of this. First, let w be any other solution of the system of linear equations xw equals y, other than the least norm solution that we previously defined. And therefore, what we can say is that the matrix vector product x times the vector constructed from the difference between our new solution and our least norm solution must equal 0. So this is very straightforward. The new vector that we get, w minus w least norm, it's a vector of non-zeros. However, x times w is equal y, x times w least norm is equal y, and so their difference has to equal 0. Therefore, the previous vector delta in the null space of x that we discussed is now equal to the difference between our new solution, which can be any new solution, and the least norm solution. So this vector is delta from the previous slide. So this is an important fact. Also, what we can show that the dot product between delta, which is our w minus w least norm, so this vector dot product with the least norm solution is equal to 0, meaning that the vector constructed from the difference between any solution and the least norm solution is orthogonal to the least norm solution. So how can we show this? It's, as you can see, requires 2 lines. We replace this least norm solution with the equation for it from the previous slide. We're not going to do that for this least norm solution, but for the second least norm solution, we're going to replace it with this, which is what we define the least norm solution to equal. And then we take this term and represent it as a matrix vector product transposed. So again, by the rules of matrix vector products, if we take this matrix vector product and transpose it, that's equal to the vector transpose times the matrix transpose. But when we write it this way, we can see very clearly that because the difference of these solutions is in the null space of x, because x times w equals y by definition of our choice of y, and x times the least norm solution is equal to y by the proof of on the previous slide, the difference of those two vectors is equal to 0. So no matter what this equals, we have a 0 vector dot product with some other vector has to equal 0. So it's very straightforward. We've shown that the difference between the least norm solution and any other solution is orthogonal to the least norm solution. Okay, so let's finish up the proof. So we have the squared norm of our solution. W is any vector that satisfies this equality. There are an infinite number we can pick from, and W is any one of those vectors. Trivially, we can add a vector to that vector and subtract it off again. So we add the least norm solution and then subtract it right off again. And so these two are clearly equal. However, now think of these two the difference of these two vectors as a new vector. And so think of this as one vector and this as a second vector, and then expand this term. So by expanding this term, we can show that the square of the sum of these two vectors, so this is one vector plus a second vector, is equal to the square norm of the first vector plus the square norm of the second vector plus 2 times the dot product of those two vectors. So by expanding this out and treating this as one vector and this as a second vector, we get this sum of 3 terms. However, now notice that by our derivation above, we can say that the dot product of the difference between our new solution and the least norm solution with the least norm solution is equal to 0. So we've shown this no matter what solution we pick for W, that this dot product is equal to 0. And so what have we shown? We've shown that the squared norm of any solution that we choose is equal to the sum of 2 terms. It's equal to the squared norm of our least norm solution plus the squared norm of the difference between our least norm solution and any other solution that we choose. So of course, these 2 terms have to be non-negative. So what we have is the sum of a positive number with another positive number. I almost dare I say trivially, we can say that that's got to be greater than just one of those numbers. So if we add 2 non-negative numbers, that the addition is got to be greater than just one of those numbers. And so the sum of these 2 numbers is greater than the squared least norm solution. Therefore, we've proven that any solution that we choose has got to be greater than the least norm solution. And it all hinged on the fact that any solution that we choose has a dot product that results in 0. And the only way that we can get this term to equal this term is if we set this term equal to 0, meaning we must select W to be our least norm solution, then we satisfy the minimum.